So we've now proven that for natural numbers n, 0 is less than next n. And we do have this property here, which says if you see a less than and then a next, you can mush them together and turn them into a less than or equal to. So this is actually equivalent to saying 0 less than or equal to n. So that's really what we're saying. Given for any natural number, 0 is less than or equal to it. So in other words, 0 is the least natural number. This is a way of saying something is the least, right? Is to say it's less than or equal to all things. So that's what these two are saying. 0 is the least natural number. You can think of this also as being a part of that statement, is that 0 has no predecessor. So when I use the word predecessor, that's like the opposite of successor. Successor, that's defined up here. Successor means next. That's what's meant by successor. So successor is like what comes immediately after. So like 3 is the successor of 2, right? And then 4 comes after 2 in some sense, but I wouldn't say 4 is the successor of 2. 3 is the successor of 2. Just another way to state this relationship, that 3 is the successor of 2, is to say that 2 is the predecessor of 3. So 2 is the thing immediately before 3. And what we're saying here is 0 has no predecessor. So 0 is not the successor of anything. 0 has no predecessor. Now, to prove this, we'll have to break the rule just once of only using this whenever we need to do something with order or succession. So here's the proof. You'll see where we break that rule a little bit. Proof by contradiction. So suppose 0 did have a predecessor. So just suppose for the sake of contradiction, let me not write out the whole thing. Let me just talk it through. Suppose for the sake of contradiction that 0 is actually the next of something. So that we have some n, who knows what it is, and 0 is the next of it, and n is a natural number. Well, then since 0 is less than the next of any natural number, we would have 0 is less than 0, right? Well, what's the problem with that? Why is that? I mean, that sounds like a contradiction, but exactly what's the contradiction? Well, to see the contradiction, I have to break my rule of only using the essence of type result and go back to the original set theoretic definition of less than, is that it's just a fancy way of writing membership. So this is the same as saying 0 is in 0. And 0 in the first place is a fancy way of saying the empty set. So this is like saying 0 is in the empty set. And that contradicts the fact that the empty set is empty, theorem 12. So nothing is in the empty set. And so 0 in particular, which is the empty set, but it doesn't matter, 0 in particular cannot be in the empty set. So that's the contradiction. Hence, 0 cannot have a predecessor. So that's kind of an exception to the rule. And because of that exception, I feel like it might have made sense to put something like this up here as one of the essence results. Maybe it could be part of the essence of 0 or something like that. But I feel like it belongs with the other stuff that's related to 0. So typically you will not be using this definition. That was kind of an exception. Typically this will have everything you need, and avoiding the definition and trying your best to just use this will help you avoid overcomplicating things. Alright, so you can think of this statement, 0 has no predecessor, as a way of saying that if something has a predecessor, if a natural number has a predecessor, then it must not be 0. Right? That's like the contrapositive. If a natural number has a predecessor, then it must not be 0. The converse of that is also true. If a natural number is not 0, then it has a predecessor. That's what theorem 98 says. So we should be pretty happy that theorem 98 is true, but I'm actually going to recommend that you skip reading over this one. And the reason for it is that it's kind of a terrible example of induction. It just does not go the way induction normally goes. And unfortunately, it's the second example we run into. The first example where we use induction is here, in the proof of part 1 here, and then this is the second example. It's just a terrible early example to see because it's very unconventional. So I would say definitely skip this. It just fits here in the logical order of things, but we're actually not going to use it very much. So please skip. And move on to Theorem 99. All right, so I think the lecture has run to the end of the allotted time already, so we'll do this one next time. So please read up to, at least read through Theorem 97, read up to here. And I think the homework that I gave you is exercise 114. We didn't get that far, but you can just save that for next time.